This video presents a botnet introspection system which investigates botnet behavior by inducing malware traffic. What is a botnet? A botnet consists of widely distributed bot clients which are infected by malware and constitute a source of malicious activities on the Internet. Once a victim host is infected by a bot program, the host contacts a CNC server, which relays malicious orders, for example, DOS, spam, etc., from a botnet manager to the victim host. The botnet manager injects their malicious orders into CNC servers to propagate the manager's order over his botnet. When the malware victim receives that malicious order, it pursues malicious behavior as ordered. Next, we will explain the detailed behavior of malware. A victim host, which is infected by a bot program, tries to communicate with CNC servers. We will discuss how the host finds the CNC servers that they are going to contact. First of all, the victim host connects to a rendezvous CNC server which knows other CNC servers. Then, that rendezvous CNC server tells the IP address of an actual CNC server to the host. However, if the bot program statically contains IP addresses or domain names of rendezvous servers, some security enforcers, like a public section or security vendor or an ISP, can take down these rendezvous CNC servers by analyzing the malware program. Therefore, some bot programs use dynamically generated domain names which are difficult to predict. This type of bot program is called the Domain Generation Algorithm Bot, or DGA for short. This is the bootstrap sequence of a DGA-type bot program. The bot program generates domain names by using their generation algorithm, which uses some random seeds, such as the current time of day. The botnet master can predict these domain names because they know their generation algorithm. Hence, the botnet master previously registers their rendezvous CNC server's IP address to the DNS as the predicted domain names. The bot program resolves their generated domain name to the IP address of the rendezvous CNC server. The bot program can access rendezvous CNC servers to find other CNC servers. As previously shown, current bot programs use DNS mechanisms to connect their botnet families. Botnet programs have to use a DNS cache server to resolve domain names. We use specially prepared DNS cache servers to redirect instances of access from botnet programs to our decoy server. Our DNS cache server has a malicious domain name list. If there is a queried domain name on the list, the server rewrites an IP address in the DNS response to our decoy server's IP address. Hence, the bot program accesses our decoy server instead of the real rendezvous CNC server. Our decoy server acts as an HTTP transparent proxy server. The decoy server can selectively relay their HTTP requests or responses by using a configured rule set, and can record all transactions between the bot program and the CNC server. Our introspection system needs DGA domain names to detect the malicious behavior of bot clients. In this section, we will explain a dynamic analysis system to collect DGA domain names. We are using a malware sandbox to detect malicious domain names. We use the Cuckoo sandbox as the analysis environment. The Cuckoo Sandbox is a malware analysis platform which uses virtual machine technology. Cuckoo can trace and record OS-level API calls, network traffic, and memory dumps on the virtual environment. It can reveal the behavior of the targeted malware. This is an example of the workflow. In this case, we are running the Game Over Zeus malware in the sandbox. To connect to the botnet, the malware generates a DGA domain name to contact the botnet CNC server. The Cuckoo hypervisor observes and records every domain name query from the malware. Malware sometimes sends queries of legal domain names to check its connection state. Hence, we extract such legitimate domain names from observed domain names using whitelists. As a result, we can get a malicious domain name list which contains botnet CNC server names. This chart indicates the result of our introspection system. Almost 20,000 connection attempts are observed by our system per day. Although there is a significant amount of connection attempts, almost all of the connection attempts cannot make the connection successfully. This result shows that the malware generates many kinds of DGA domain names, but the botnet manager only uses a fraction of them. Next, we will focus on successful connections. In most connections, malware clients perform POST to send their information to botnet CNC servers. However, these connections were mostly terminated by error code 404, not found, or 403, forbidden. This behavior indicates that IP addresses associated with malware domain names are not always real CNC servers. Sometimes, botnets frequently change their CNC server hosts to obscure their behavior. The subsequent slides will now explain a potential application scenario of this system. Our platform provides a pipeline which can connect data sources, analysis modules, and mitigation systems. In this scenario, we used several kinds of analysis modules to detect malicious DNS domain names. One of these analysis modules is the dynamic analysis system explained earlier, and the other is a Lynx DNS traffic analysis module which detects malicious domain names from live DNS traffic using machine learning technology. The result of each module is stored into Matatabi, which is a distributed computing platform based on Apache Hadoop software. The stored data is shared in the Necomatter system, which facilitates information exchange among operators, analysis modules, and mitigation modules. Necomatter is designed to promote interactions among multiple operators, multiple analysis modules, and multiple mitigation mechanisms. This is a screenshot of Necomatter. It looks like a timeline-based SNS service. Each analysis module posts a summary of their analysis. A user can also post their messages to the timeline. This is the overview of the Necomatter system. Each analysis module periodically analyzes collected data sources, and the modules post the results of their analyses to Necomatter. Operators can examine the detected threat information, and they can order some command modules to stop particular threats by posting commands into the timeline. Command modules are watching the timeline, and when there is a post from operators, they apply the designated commands. Hence, an operator can carry out all of their security operations on our Necomatter platform. This is an overview of our demonstration scenario. A host which is infected by malware initiates an occurrence of malware traffic. On the other hand, our dynamic analysis module detects malicious domain names and stores this information on the Matatabi platform. This information is also shared in Necomatter. Then, the mitigation module receives threat information via Necomatter. Next, mitigation modules apply a filtering according to the received threat information. Lastly, the malicious traffic is blocked by that filter. From this point, we will discuss the results of our demonstration. The analysis module periodically posts detected malicious domain names on Necomatter. The mitigation module receives malicious domain names from Necomatter, and the module applies filters to block these domain names. This bar chart shows filtered DNS queries. Our mitigation module successfully filtered out these malicious DNS queries from the network.